Hello friends, so welcome to module 17 of this course Essential Mathematics for Machine Learning. This particular module is in continuation of the last module in which we have introduced to you about principal component analysis. And then we have seen that the principal component directions are nothing just the direction given by the eigenvectors of the covariance matrix which we have taken from the data. Then we have to reduce the dimension of a data from, let us say, n to k, where k is less than n. Then what we need to do? We will take first k largest eigenvalues of the covariance matrix, and then their corresponding eigenvectors will span the subspace. By projecting the n dimensional data onto that k dimensional subspace, will reduce your data with dimension k. At the same time, it will preserve as much randomness or variance as possible in your data. So, let us drive it first mathematically. So, it is a bit mathematical, but very interesting. So, the objective of PCA is to perform dimensionality reduction while preserving as much of the randomness in the high dimensional space as possible. So, for this, let x be an dimensional vector such that x equals to I equals to 1 to n y I phi I, where phi 1, phi 2, phi n forms an orthonormal basis of n dimensional vector space in which x lie and the coordinates or the weighting coefficients y I are given as. So, y I will become your inner product of x with phi I. We have seen it earlier. In case of R n, it will become the dot product for all I equals to 1 to n. So, this is the representation of a vector x in n dimensional space. So, what we are taking an orthonormal basis. So, phi 1, phi 2, phi n are basis vectors, and we are taking the linear combination of these basis vectors to represent the x. Now, suppose I want to represent x with fewer basis vectors, that is say m, where m is less than n. So, how we can do this? So, we can do this by replacing the coordinates ym plus 1, ym plus 2 up to yn with sum of pre-selected constants BIH. So, xm means I am representing the same x, but in lower dimensional space having dimension m. It will become I equals to 1 to m yi phi I plus I equal to m plus 1 to n bi phi I. Now, the representation error is so let me denote this representation error by del xm. Then this del xm becomes x minus x cap, means this is the x represented in the higher dimensional space and this is in lower dimensional space, that is with m basis element. And if you use this equation, let us say equation 2, and this is my equation 1. So, by 1 and 2 this will become I equals to m plus 1 to n yi minus bi phi I, because first term will be cancelled with first m basis elements. Now, we can measure this representation error by mean square of the magnitude of the difference, that is delta x. That is, I am defining this error as E delta x square, that is the mean square of the magnitude of x, and this will become E times summation from m plus 1 to n and summation on I and square of this. So, it will become E of m plus 1 to n yi minus bi and then phi I, since square is there. So, I will write m plus 1 to n yi minus bi phi I, and this will become E times If I take this summation together, I m plus 1 to n and j equals to m plus 1 to n, and then what I am having, yi minus bi, yj minus bj, phi I transpose phi j. So, I have opened this summation and I got this one. Now, phi 1, phi 2, phi 3 all are orthonormal bases. So, when I not equals to j, this dot product of these two basis elements will be 0. Otherwise, if with the same, if both are equal, I equals to j, it will become 1. So, in that way what we can have, we can write the mean square error of the representation error equals to I equals to m plus 1 to n, and expectation of yi minus bi square. In PCA what we need to do? We need to find out bi as well as phi I, which minimize this particular error, because it is the representation error and we want to preserve as much as information in lower dimensional space. So, what we need to do? We have to minimize the representation error. So, now first find bi. So, for finding bi, I will be having del E upon del bi equals to 0, and this will give me minus 2 times E of yi minus bi equals to 0. This means bi equals to E times yi. So, now substitute this value of bi here. So, what I will be having, E of delta x square equals to summation over I from m plus 1 to n E of yi minus E of yi, and then square of this, and where yi is given by x transpose phi I. So, substitute this value here. So, then I will be having E of delta x square equals to summation I equals to m plus 1 to n, and then I am putting this value here. So, E of x t phi I minus E of x t phi I and square of this becomes summation phi I transpose E times x minus Ex x minus Ex transpose and then phi I. Now, if you see carefully, what is this? It is the data covariance matrix as per the definition of covariance matrix. So, it is the data covariance matrix. So, what I can write? The mean square of the representation error equals to I equals to m plus 1 to n phi I transpose sigma x is the data covariance matrix phi I. So, let me give equation number 3. Now, what I have to find out phi I. So, to find phi I, what I need to do? Del E delta x square upon del phi I equals to 0 and subject to phi I transpose into phi I equals to 1. Since I am having this condition also, I have to minimize this. I have to find out phi I means I have to minimize, and for over phi I E del x square subject to phi I transpose into phi I equals to 1, since they are the orthonormal basis. So, by using Lagrange multiplier, what I can write? I can include this condition here. So, minimize phi I transpose covariance matrix into phi I plus I equals to m plus 1 to n lambda I times 1 minus phi I transpose into phi I. And then if this is j phi I, then to minimize it, del j phi I over del phi I equals to 0, and this will give me sigma x phi I equals to lambda I phi I. So, 4. So, now this value of sigma x phi I substitute here. So, basically what is phi I and lambda I first? They are the eigenvalues. So, here phi I and lambda I are the eigenpair of the covariance matrix. Now, from 3 and 4, we have E delta x square equals to summation I equals to m plus 1 to n, and then phi I transpose into lambda I phi I, and this becomes I equals to m plus 1 to n lambda I, because phi I transpose into phi I will become 1, and for when I not equals to they will become 0. So, now mean square of the representation error is sum of the eigenvalues. So, what I need to do here? So, in order to minimize the representation error, which is mean square, lambda is need to be smallest eigenvalues. Means what I need to do? I am having n eigenvalues. Out of n, I have to choose n minus m minus 1 eigenvalues, and some of those should be the minimum. So, what those n minus m minus 1 eigenvalue I will choose? I will choose the smallest one, and I will ignore them, and hence to minimize the representation error or preserving the maximum variance, maximum randomness in my data after projecting into lower dimensional space, I have to select only eigenvectors corresponding to larger eigenvalues. So, this is the meaning of this. So, means what we conclude from this derivation? Therefore, in PCA we choose m eigenvectors corresponding to the m largest eigenvalues lambda I of the covariance matrix. Sigma x as the principal directions. So, this is the proof why we are taking principal directions or principal components in the direction of eigenvectors corresponding to largest eigenvalues of the covariance matrix. Now, one more important thing, what is the relation of PCA with SVD? So, PCA and SVD. So, let the data matrix be C of size n by p. So, means I am having n number of samples and each one is having p direction. So, my data original dimension is p. Then the principal directions and therefore components are coming from the eigenvectors of the covariance matrix. So, sigma c, and that is 1 upon n minus 1. So, sometimes we can write 1 upon n also, but in variance generally we write 1 less C transpose into C, which is a P by P matrix. Now, if the SVD of C is given as C equals to U S V transpose, then the covariance matrix is 1 upon n minus 1 C transpose into C. So, 1 upon n minus 1 and then C transpose is U S V transpose into U S V transpose, and this comes out to be 1 upon n minus 1. So, this will become V S U T into U S V T. So, V S square and V T. So, since this covariance matrix is a symmetric matrix and V is an orthogonal matrix. So, what I am having now? This is orthogonal diagonalization of sigma. So, what are the eigenvectors of sigma? The columns of V are the eigenvectors of sigma. And what are the eigenvectors of sigma? They are the principal directions, they are giving you the principal components. Therefore, if the SVD of the data matrix is C equals to U S V transpose, then columns of V give the principal direction. And then if you want to project, then it will become XV, and XV will be US, so not XC, CV, sorry, CV US VTV, US gives the principal components. Furthermore, how much information I have preserved, that you can see from here. So, this much information we are discarding. So, information preserved is, if you are coming from n dimensional space to k. So, lambda 1 plus lambda 2 up to lambda k upon lambda 1 plus lambda 2 plus lambda k plus up to lambda n, and all are absolute value. Into 100 will give you the percentage of information preserved in your data. Okay. So, now let us take some example. So, example 1. So, compute the principal components for the following two dimensional data. So, data is x equals to x1 x2, and these are points given by 1 2 3 3 3 5 5 4 5 6 6 5 8 7 and then 9 8. So, means what I am having x1 column, x2 column, and then data is 1 2 3 3 3 5 5 4 and so on 9 8. So, first what I need to do, this is my data matrix. So, 1 2 3 4 5 6 7 8. So, it is 8 by 2 matrix. This is the matrix C. First I have to find out sigma C, that is the covariance matrix, that will become 1 upon 7, means 8 minus 1 7, 8 are the sample point, C transpose into C, and this comes out to be 6.25, 4.25, 4.25, 3.5. Now, eigenvalue of this is lambda equals to 0.4081 and 9.3419. So, eigenvector corresponding to this eigenvalue means 0.4081 is 0.5883 and for second one is 0.8086. Similarly, eigenvector for corresponding to this is 0.5883, 0.8086. So, these eigenvectors are giving you the direction of principal components or principal directions. So, if I want to reduce this data into one dimension, then that one dimension, if data is y, will become, because this is the larger eigenvalue. So, this will be the principal direction. So, 0.5883 x1 plus 0.8086 x2. All these pairs will project it to 1D, that will be our y. So, if you want to see, this is the example, these are these points I have plotted in 2D, and this green one is giving the direction of principal component, while the second one is the another eigenvector. Another example, consider this again 2 dimensional data x and y, and I am having something like 2, 3, 4, 5, 6, 7, 8, 9, 10 sample points. First, what I am doing? I am shifting the center of this data to the origin at 0, 0. So, what I need to do for this? Means I want 0 mean of the data. So, what I need to do? I have to subtract the mean of x from all these entries and mean of y from all these entries. So, after doing this, you are getting this data. So, this is the original data, this is the data with 0 mean. So, just subtracting from each column their respective mean. Now, from this data what I will do? I will find out the covariance matrix, and covariance matrix comes out to be this one. Now, I will find out the eigenvalues and eigenvector of this. So, eigenvalues are 0.04908 and 1.2840. Similarly, eigenvectors are these one. So, this is the bigger eigenvalue. So, this is the direction of principal eigenvector. So, if I want to reduce this data to 1D, so I have to write all the data, that is x, y given originally as the linear combination as 0.677 x1 or x plus 0.735 y. And if I do this, you can see this is original data and this is one dimensional data, means after projecting on the principal eigenvector. So, in that way you can reduce the dimension of your data. Suppose your data is having a dimension 100, you want to reduce it up to 20. So, what you have to do? You will find out the covariance matrix, that will be 100 by 100 matrix. You will find the eigenvalues of that covariance matrix. So, 100 eigenvalues, you will select top 20 eigenvalues corresponding eigenvectors. So, those will be orthogonal to each other. So, those 20 eigenvectors will give you or will span the 20 dimensional space, and if you project your 100 dimensional data to those 20 dimensional space, your data dimension will reduce to 20. So, this is all about principal component analysis. So, these are the references. In the next lecture, we will learn another very useful concept, that is called linear discriminant analysis. Why we need linear discriminant analysis when we are having PCA type of thing. So, thank you very much.